This is a Brownian motion question. The first part asks you about the conclusions drawn from Brownian motion, in this case, the pollen grains suspended in the liquid. The molecules of the liquid are in random motion. You must say either random or hazard to gain this mark. They do not allow zigzag. The molecules of the liquid are smaller than the pollen grains. You must compare the molecules to the pollen grains and cannot say that the mass is smaller. The second part is only worth 1 mark, as they only require you to say that if you increase the temperature of the liquid, the motion of the pollen grains would be increased. Part B is ultimately a definitions question, as you are asked to list the 3 assumptions of the kinetic model of an ideal gas. Remember to spell all your terms correctly. Collisions with the walls are elastic. You must refer to the walls of the container, and any reference to collisions between molecules will be ignored. The forces between molecules are negligible except during collisions. Make sure to say the phrase except during collisions. The volume of the molecule is negligible compared to the volume of the container. You must use the terms molecules and compared to gain this mark. The time within a collision is negligible compared to the time between collisions. You must say the phrase compared to the time between collisions for this mark. The second part of B asks you to explain how a gas exerts a pressure on a container. The momentum of the molecule changes when it collides with the wall. You must say that it is the momentum of the molecule that changes, and you must mention wall. The mark scheme will also accept that there is an impulse on the molecule when it collides with the wall. The force on the molecule is the rate of change of momentum by Newton's second law. You must refer to the molecule for this mark. The force on the wall is equal and opposite to the force on the molecule by Newton's third law. For Newton's third law, the necessary words are wall and molecule. Pressure equals sum of forces due to all molecules divided by the area of the wall. For this pressure equation, you must say that it is the sum of all forces.